All right, may I have your attention? I will answer the question in the quiz. Actually, there will be several quizzes very similar in which you will have to describe or to explain what is a particular device. And the answer will be always very similar. First, you have to say what it is. Well, this is the answer. I mean, what kind of an object it is, right? So capacitor, for example, is an electrical element. You can also say that it has two sides, although I won't require that. And important thing is, what does it do? So capacitor is an element for which potential difference between the two sides of this element is proportional to charge transferred from one side of this element to the other side of this element. You can also say charge stored. I will accept that. However, whenever you say charge stored on a capacitor, you have to recognize that it refers to charge which is transferred from one side to the other side. The total charge of the capacitor is always 0. All right. Now, probably I should mention something here as well, because I know that a lot of you have this type of a common knowledge which states that current, whatever it is, we will learn in the future what it is proportional to voltage, which properly is referred to as potential difference. So here you have an example in which it is not true. It is, for most devices, current and voltage are not proportional to each other. For example, in a capacitor, what is proportional to the voltage? In other words, to potential difference between the plates. It's not current. I have never mentioned the word current so far. What is proportional to potential difference? Charge transferred, correct. So be careful in the future, because I know that a lot of you have this knowledge from high school. You discuss just one element in high school, a different element than capacitor, for which indeed potential difference is proportional to current. By the way, anybody remembers what was that device from high school? For a resistor, correct. In a resistor, this is true. We will talk about resistors in the future too. I mean, probably even tomorrow. No, not tomorrow. Tomorrow we have a test. Oh, I think that you would be probably interested. So I will I will preemptively answer the question. On tomorrow's test, we'll have descriptions of electric field as the region. And we have two functions which describe electric field. This is electric field vector and electric potential. Now, physics, like all engineering, is a subject in which actually you have to remember everything what you learned before. So I assume that you understand physics 1, mechanics and thermodynamics. So on the quiz there will be questions which will refer to physics 1. You will have, because now describing electric field in terms of electric field vector leads to a certain quantity which describes interaction between objects. That quantity is directly, I mean, very straightforward. If we multiply electric field by a charge of a particle placed at that location, we will get, I mean, electric field vector. If you multiply electric field vector by a charge of a particle placed at a particular location where we know electric field vector, we will get what? The force. Which force? The electrostatic force, correct. Well, now remember that this is one of the forces, so make sure that you refresh your memory how to draw a free body diagram, because one of the problem will be a static problem in which you will have several forces, and among others there will be an electrostatic force and you will have to figure out what will happen with the system. All right. Now the second description of the electric field was electric potential, which leads directly to another description of interaction. Which one? Work, and then through work energy theorem, you can figure out what will happen with the object. One problem will be based on that. And actually, in this problem, as I remember, you will also have to kind of translate from a description of the electric field in terms of electric field vector and electric potential. So make sure that you know both ways. If you know electric field vector, how to find electric potential, and if you know the distribution of electric potential, how to find out electric field at a particular location. You will have to do it. The last problem, the most difficult problem, and I know that although objectively it isn't, or conceptually it is not the most complicated task. However, you are still struggling with integrations. So the fourth problem, I consider that it will be difficult because it will require integration. Make sure that you refresh your memory from calculus about first fundamental theorem of calculus and how to use indefinite integral to find definite integrals. I will give you an object of a certain shape, and I promise that it will be a linear object, so it will be a single integral. So not surface or not volume. I will give you. I mean, in the problem you will have either charge density, linear charge density, and you will have to find out charge and let's say electric field vector at a particular location or electric potential at a particular location. I can also give you charge and say that it is uniformly charged, so you will have to find out linear charge density, and again find electric field vector and electric potential at a particular point. So the last problem, I try to arrange the problems in an order from the simplest to the most difficult. Problem number one. For problem number one, review the quizzes, because problem number one is always about defining or explaining things, I mean relations. So definitely now think what definitions I could put on in problem number one. No, I promise capacitors or devices won't be on the test. Only the descriptions of field. So whatever I discuss this week won't be on the test. Only electric potential and electric field vector, calculating those and figuring out what will happen to particles when they find themselves in that field. So definitely I will ask one question, which without that we wouldn't resolve the quiz, not the quiz, the test. Carl, why don't you remind me a definition which you think that is really very important to this section of material? Electric field vector, correct. What is electric field vector, for example? This will be definitely a question. Another question will be obviously what is electric potential. Yeah, because you have to know those two things. All right. So this will be all for. Oh, by the way, one more thing. I mean, those of you who had class with me, then it is clear for you. I mean, you know about, but those who are here for the first time. So this is your first test with me. I'm not interested in the answer. I'm interested in the solution. So it has to be clear. basically try you don't have to be as detailed as in homework, so be a little bit briefer with that. However, whenever you bring up a formula, make sure that you identify what formula you use. So don't say, I use formula, because then you can use any formula. You can write down whatever you want. Yes, so say, from Coulomb's law, for example, or from definition of electric field vector, from definition of electric potential, for linear charge density. Make a statement which introduces the formula what you write. I want to have text in the test. Now that test has to have two functions. You have to explain what is what of what, and you have justify applicability. Why is it applicable? Yes, so for example, if you have a rod of a certain, and that rod has certain charge, you cannot use a formula for electric potential of produced by a particle. Why not? Because it's a wrong object, right? The formula for potential KQ over R is applicable for particles, not extended objects. Also, I give a lot of credit for making appropriate drawing. So make sure that the drawing is clear and informative and relevant. So don't draw cartoons. All right, so this will be all about the test. Oh, let's go through that. Now, we know already what a capacitor is, so I would like to talk a little bit about this, how to make it. Because, well, so far we said that it has to perform in a particular way, that the charge transfer from one side to the other side is proportional to potential difference. And, well, although, I mean, in order to understand how a capacitor is built, actually we will analyze a particular type of a capacitor referred to as parallel plate capacitor. And parallel plate capacitor is made from two parallel conductive sheets separated by a dielectric. And actually dielectric in many cases makes also this device stable, so it can be assembled together. All right, so now how to check if this is a capacitor? What would we have to verify now? We have to recall what is a capacitor. Andrew, what is a capacitor?
Object that's stored charge or...
No, it doesn't store charge.
Well, sort of separation of charge.
It's not important. It's one of the functions, and it is rather rare function. Because I mean, if it this is a misconception. The capacitors are used for storing charge. It's rather rare application. It can happen, but when it is stored in the sense that it is transferred from one side to another side. So then, when we make appropriate path, we can force that charge to flow from back. Back to from one plate to another plate. This is not important that it stores the charge. Something else is more important. Christy, what is it? Well, no, because we have a lot of electric elements, so it doesn't make it a distinction. No, not two conductors. The potential difference is proportional to charge transfer between the plate. This is what makes a capacitor a capacitor. All right, so let's see if in this device we would really have that relation satisfies. So let's say that let's say that the dielectric has dielectric constant of value kappa, that the area of each of the plates is 8, and the separation between the plates is d, because actually these three parameters are going to determine what kind of capacitor. In other words, what will be we will find out that capacitance will be determined by these three numbers. All right. So now we have to see if potential difference between one plate and another plate, this is potential difference, is proportional to charge transferred. So I have now to see if this quantity, potential difference between the plates, is proportional to this charge. All right. Well, from the relationship between electric field and electric potential. Well, first of all, let's start. Two parallel plates will produce what type of electric field? A uniform electric field. Yes, so for uniform electric field, it is actually easy to find out that potential difference by integrating the relationship. Let me remind you that relationship. Difference in potential, differential difference in potential between two consecutive points along a certain path is opposite to scalar product E times ds. So if I apply it to that uniform electric field, and for simplicity I can take a path which is perpendicular to the plates, I will find out, if I integrate that expression, I will find out that potential difference between one plate and another plate is equal to the product of the electric field strength between the plates, which means the magnitude of electric field vector, and the separation between the plates. It is a useful relationship, so make sure that you remember it for tomorrow too. If you have a uniform electric field somewhere tomorrow, you don't have to integrate it. You can just recall that relationship. However, if you don't remember, just integrate it and you will get it. All right. Now, electric field strength between the plates is dependent on the charge density. Do you recall that? I mean, in front of a single plate, we had that it was surface charge density divided by 2 times permittivity of free space. Right? Now, since we have 2 of them, we have to multiply it by 2. So if we didn't have dielectric, the electric field strength between the plates would be just surface charge density divided by permittivity of free space. This would be electric field without, this would be electric field strength without the dielectric. Now recall that when we place dielectric, we have to divide that by dielectric constant of the substance in order to get the resultant field. So what we have over here is the electric field strength between the plates in the presence of the dielectric. Now, surface charge density, on the other hand, is related to the area and the charge. So instead of having surface charge density, I can write down that it is charge on that top plate divided by the area. Where should I go next? Nowhere. That's it. Yeah, what was I supposed to shout?
It's proportional to
that potential difference is proportional to the charge transfer. Right? Look that all those quantities here are certain constants. For a given capacitor, we have a certain separation between the plates. Dielectric constant is a constant which depends on this what I put between the plates. Permittivity of free space is a universal constant, and for a given capacitor, the area is also fixed. So we have proven here that indeed potential difference between the plates is proportional to charge transferred from one plate to another plate. It means that this device is a capacitor. All right, so I shrank this, the relationship. We have the potential difference is proportional to capacitor. And here are examples of how capacitors are made. This one indeed has two metallic plates, probably aluminum plates, separated by a thin layer of a dielectric, and then they are packaged in this plastic. So it is a firm device now. And indeed, this one is a parallel plate capacitor. I can imagine that the two plates are facing each other. Here's another example of a parallel plate capacitor, which on top of it is variable. By turning this knob over here, we can change the surface. The surfaces facing each other. So sometimes if you pull it out, the capacitor will have a smaller area. So it's a capacitor with variable capacitance. Now, although these capacitors don't have parallel plates, but we can imagine that the plates are just wound into a spiral, and still this relation is going to be applicable. Now this capacitor actually is even electrolytic capacitor, which is not made from two metallic plates. It is there is only one metallic plate, and then there is the other one is made in electrolyte. Advantage of this capacitor is that the plates are separated by a very small distance. All right. Yes. So in conclusion, that coefficient which related, I mean, on the previous slide, the inverse of the coefficient which was in the previous slide is capacitance. Yeah, because proportionality coefficient between potential difference and the charge, and more precisely it is that charge transferred from one side to the other side, in other words, charge stored on the capacitor, is equal to capacitance multiplied by of the capacitor multiplied by potential difference across the capacitor. Now, on the previous slide, we had the coefficient in front of charge. Therefore, I had to move it to the other side. And after I did that, I got an expression for capacitance of parallel plate capacitor. And we see that capacitance depends on the what type of material we use for the dielectric and the shape of the capacitor, area of the plates, and distance between the plates. All right. Let me start with a certain misconception, because probably a lot of you also have this misconception that capacitance says how much charge can be stored on a capacitor. Who believes that? If you don't, you are good. Because let's try then, I take a 1 millifarad capacitor and think, and so let's say that I have a capacitor, that capacitance is 1 millifarad. How much charge I can store on this capacitor? I'll give you, let's say, 15 seconds to discuss with each other, so, or maybe 30 seconds. talk to each other now. How much charge can be stored on a 1 millifarad capacitor? Talk to each other. Go ahead. Okay. So, what's your opinion? Okay, Lee over there has an opinion. So, not system. Well, depends. But what do you mean by system? The capacitor, probably. Yeah, it depends on the voltage applied to that capacitor or produced between the plates of the capacitor. All right. Yeah. So how much? I mean, I can do with voltage whatever I want. I just need to use a power supply appropriately, and I can adjust voltage. So how much charge I will be able to store? Whatever voltage I can produce, right? Now, for a given capacitor, if you go to a Radio Shack or electronic supplies and you look what is written on the capacitor, there are two parameters written on the capacitor. One is indeed capacitance of the capacitor, which will say how the capacitor is going to behave in a circuit, and the other thing is maximum voltage which can be applied to this capacitor. So, for example, it could be 100 volts or 1 kilovolts or even 10 kilovolts on some capacitors. So, what is the maximum charge will be the product of that maximum voltage which can be applied to the capacitor and the capacitance of that capacitor. Now, what is the maximum voltage depends on the dielectric which is between the plates, and more precisely it depends on the dielectric strength of that substance. And dielectric strength of the substance is the maximum of electric field strength that will not cause a breakdown of the dielectric. A breakdown of the dielectric happens when the dielectric stops being an insulator and allows current to flow. So, for example, a dry air will have a dielectric strength of 1,000,000 volts per meter. So, if potential difference between this point and this point is this is about 1 meter. If it is 1,000,000 volts, we will get a spark from one hand to the other hand. Well, if it is 1 millimeter, then it will be only 1,000 volts. Yes, so if separation between the plates is 1 millimeter and potential difference between the plates is 1,000 volts, the spark will pass through. I mean, sometimes we want it. I mean, in a spark plug, for example, we take advantage of it. The dielectric strength of air inside a combustion engine cannot handle electric field between the electrodes of the spark plug, and ignites the combustion. So the combination of capacitance of a capacitor and the dielectric strength of the dielectric separating the plates determines how much charge can be stored on the capacitor. Now, what do we understand by stored? Transferred between the plates, correct. Whenever we charge capacitor, we store energy in a form of electrical energy. Now, this will be actually more important. Capacitors are rarely used as this storage device for electricity. We have much better storage. However, if it is necessary that we need to release a huge number of energy in a relatively short period of time, that indeed we can use capacitor for that purpose. However, in the car we don't use capacitors to store energy. What device we use in a car? A battery, correct. Battery is much more practical device to store energy. For example, in high power lasers, in which we want really to deliver a lot of electricity into a pulse of light, power supplies are used first to charge the capacitors, to store energy in the capacitor, and then this energy is released in a very short period of time, sometimes even in a femtosecond time interval. All right, so let's see. Electrical energy is a potential energy, so really it depends on this where we choose the reference for potential energy. So let's say that if a capacitor is discharged, so zero charge is transferred between the plates, that this will correspond to zero potential energy stored in a capacitor. So now how to find how much energy is stored when we transfer the charge? Well, we could do it two ways. I mean, either we can calculate how much work is done by the source of that potential energy, or how much work we have to perform in order to charge the capacitor. So let's say that we let's find out how much work, how much differential work, because I mean, think about it. Let's start with this situation, and we can actually even do it calculating electron by electron. So let's say how much work we would have to do in order to transfer one electron from one plate to another plate if capacitor is completely discharged. How much work we would have to do in order to transfer that. Or also think how much work would be, how much electrostatic work would be done against the electric field to transfer the first electron. None. Why none? Because the force is zero. Yeah, electrostatic force is zero. So to transfer first electron from top plate to bottom plate would require no work, or electric field, or the plates would perform zero work on that electron. Now, how about second electron? Is that work going to be zero, positive, or negative? Let's think about work which we will have to do. Positive. The plates would perform negative work. Right now, why positive? Because if we transferred one electron, then this plate is charged negatively, this one is charged positively. It's tiny charge, right? The charge of this plate would be one elementary charge. The charge of this plate will be minus elementary charge. However, the charge would result already in electric field, or the force on the second electron. And the force on the electrostatic force on the second electron will be upward. Do you see that? So now we have to push the second electron down, which means that our work would be positive. The plates actually will perform negative work, right? Because now the bottom plate is repelling the second electron upward, and the top plate is pulling it upward. So the electrostatic force is upward, displacement is downward, so we see that this work is negative. The plates perform negative work. All right, so this is what will happen with the second electron. How about the third electron? Is it going, the work is going to be positive, negative, or zero? Who votes for positive? I will say by us. Positive, correct. This is positive. We are going to push again against those two electrons repelling from the bottom plate and two missing electrons pulling upward. Now, compare the work done on the third electron with the work done on the second electron. Which one is harder to move? Third one. Okay. Now, in order to, we could continue this process now until we charge to, let's say, 1 millicoulomb. We will have to transfer a lot of electrons. Well, it happens actually that indeed we could calculate electron by electron, but rather than doing this electron by electron, why don't we think that we transfer a bunch of electrons which have charge dq. So let's say that at a particular instant of this process, charge on the bottom plate is minus q, on the top is plus q, and we transfer more electrons whose charge will be minus dq from the top plate to the bottom plate, which is equivalent of transferring charge dq from the bottom plate to the top plate. Let's find out how much work, and since I put this subscript EL over here, it means that I'm thinking about work performed by the plates. So this electrical work will be, well, I have to multiply because it will change potential energy. So it will be opposite, well, to the change in potential energy. And change in potential energy will be potential difference. So this is V plus times dq minus V minus times dq. I can factor out dq and I will have V plus minus V minus, which will give me potential difference between the two plates. And minus is from the definition of potential energy. Recall that potential energy is defined in such a way that the change in potential energy when an object is displaced from one location to another location is opposite to the source, to the work done due to the source of potential energy. All right. Now, in a capacitor, because now when I charge, when we move this additional charge dq, potential difference obviously is going to change. So for the next dq, we will have a different potential difference. I can recognize that this potential difference varies. It's not a constant. As I move more and more charge, that potential difference grows. And however, I know that it is related to the charge on the plate. Since it is a capacitor, and in a capacitor, charge transfer between the plates is proportional to the potential difference by a coefficient characterizing the capacitor, the capacitance of the capacitor. So potential difference across the capacitor is equal to charge on the capacitor divided by capacitance of the capacitor. All right, so let's now find out how much work it would be done in a process in which I start with the zero potential difference and I will charge it to a particular potential difference. Or if I start with charge 0 on the capacitor and end up with a particular charge on the capacitor, let's say capital Q. So I have to add now those tiny works. In other words, I have to integrate. Yeah, and when I integrate, I will have to make sure that I account for every piece, every charge which is transferred only once and nothing else. All right. So when I specify the limits, so the limits would be, all right, so this is from definition of potential energy, from the initial charge to the final charge. Now, this is easy to integrate because it's a linear function, so it is variable squared by 2. 1 over c is a constant. I can factor it in front. And if I use fundamental theorem of calculus, I need to take indefinite integral and plug in the values of the limits. So if I do that, I will find that energy stored in the capacitor is proportional to the square of the charge on the capacitor. And then I have, in the denominator, I have 2 times capacitance of the capacitor. I can also express this potential energy in terms of potential difference because, well, I can recognize that charge divided by capacitance gives me potential difference across the capacitor. So I can also write down this formula that is charge times potential difference on the capacitor divided by 2. Or I can even go further and now if I multiply and divide this Q by this charge by the capacitance, I will get again potential difference, and it is capacitance times square of potential difference divided by 2. And I think that this will be the right place to end the lecture. See you tomorrow.